Oh. No, no, okay. Oh, yeah. All right, thanks. Okay, so thanks very much. Welcome back. So this is just to illustrate something that I mentioned yesterday in the discussion session. So one of the main motivations we're going to be discussing today is the search for new light and weakly coupled particles. And the reason we're excited about this right now is kind of illustrated in this Money plot. Okay, so what this plot is showing is the energy density of a new species X when normalized relative to the energy density of a single standard model neutrino species. Okay, and so we assume that this particle at some point in the history of the universe has come into thermal equilibrium, and then the contribution that it makes to the energy density will depend on the decoupling temperature, and that decoupling temperature itself will depend on the strength of the coupling to the standard model. Okay, so the earlier the particle decoupled, the smaller its contribution, because there will be particle-antiparticle annihilations that transfer the energy and entropy to the rest of the standard model, but not to this decoupled species. And that leads to a dilution of the energy density of this particle. Just like for the neutrino. For example, the neutrino, in fact, is living somewhere around here. Here. This would be the neutrino. It's a spin at 1.5 particle that decouples at around 1 MeV and contributes 1 in its own units. Okay? So this is the strange variable delta N effective that people have defined. But particles that are more weakly coupled, you can see 9 a.m. So particles that are more weakly coupled in neutrinos will have decoupled earlier, and they have a slightly suppressed contribution to the total energy density. And in particular, there is this big suppression due to the QCD phase transition. So if particles decoupled before the QCD phase transition, they contribute about a factor of 10 less to the total energy density than particles that decoupled afterwards. So this means that at the moment, experiments are sensitive enough to measure the radiation density in the early universe at about a 10 to 12, 20% level. So constraints from the Planck satellite constraining these type of decoupling scenarios. But they're totally blind to particles that decoupled before the QCD phase transition, because there's this drop by a factor of 10. Okay? But what's interesting is that this drop is just by a factor of 10. And so future experiments will actually measure the radiation density in the early universe by precisely this order of magnitude better, we hope. Okay, and so they therefore will become sensitive to these particles that decoupled, at very early times. Then there's no more drop here if we believe that it's just the standard model in this extra species. Then there's a minimal abundance that we have to create if this particle comes into thermal equilibrium. So in particular, for example, for a scalar particle, you produce 0.027. This has become a famous number in cosmology. That's the minimal thermal abundance that's being created for a scalar particle. Spin 1/2 particle has a factor of 2 larger than that, and then a spin 1 particle a little bit larger than that as well. Actually, I should say a factor of 1/2, and then times this annoying 7/8 because it's a fermion. That's how you would connect these two numbers. Okay. So what I want to do today is actually describe in a little bit more detail what the physics of this cosmic microwave background is, so that we can understand how we try to measure this kind of signal. Okay? But the general motivation is this. Okay, so let's start. So this is a very big topic. One could give, and in fact I have before, given a 12 lecture course on all of this. Okay? So I'm going to try and compress this into 1 hour. Okay? And the way I'm going to compress this is by simplifying as much as I can. I'm going to brutally approximate, okay, to the degree that it becomes very simple, just harmonic oscillator equations and things like that. And but that will capture the physics of the microwave background surprisingly well. We're not going to lose any of the conceptual ideas, okay? We're just going to simplify the mathematical formulation quite a bit, okay? So let's actually ask, what's the first thing we see when we look at the sky? Okay, so the first thing we see when you look at the sky, so imagine we're an observer here. So we look at this surface of last scattering. We see photons coming from all directions. So for example, we see a photon coming from here. Let's call this direction unit vector n hat. And then there's a temperature fluctuation delta t in the direction n hat. Okay. So the very first thing you see, in fact, when you measure this radiation and as a function of angle, is you see a hot spot here and a cold spot here. Okay, so you see this dipolar structure where there's a hot spot in a specific direction in the sky and a cold spot in another direction in the sky, at about the level of 10 to the minus 2, I think. So this is a fluctuation 10 to the minus 2 on top of this uniform background of 2.7 degrees Kelvin. Any idea what this dipole contribution is? Exactly. So that's our motion relative to the rest frame of the cosmic microwave backgrounds. So in this picture here, we're having a velocity v that goes in this direction. So this delta t over t, in fact, is related to the observed momentum of the photon in the direction n minus the momentum of the photon in its own in the rest frame of the microwave background divided by this momentum in the rest frame. And just by the standard Doppler formula, at velocities smaller than the speed of light, this is just n hat dot v. Okay? And we can check the sign. If n and v are aligned, okay, we get positive, so we get a hot spot and a larger temperature. If n and v are anti-aligned, okay, we get a negative sign here in this dot product, and so we get a decrement in the temperature. Okay, so that's the right expression, and it has the dipolar structure that for arbitrary angles, it will vary like a cosine. Okay. Exactly. So that's the next question. So by fitting the dipole, so by measuring how hot it is here relative to here, we can actually measure our velocity relative to the rest frame of the CMB. Any guess what our velocity is? How fast are we moving right now? It's not common knowledge, maybe. You just guess. Yeah? Sorry? 0.1 in C? Okay. Slower than that, I think. But, so per hour, I'm not. Maybe that's true. I have it in kilometers per second. So it's 368 kilometers per second. So that's pretty fast. Every second, 368 kilometers. Okay. But this is kind of a boring effect. We're not really interested in. I mean, it's nice as a trivia knowledge or something like that, but it's not really what we use. And so what we'd like to do is, in fact, remove this dipole. So removing the dipole leaves us the so-called primordial anisotropy. These are the things that we really believe come from the early universe. And that's what we want to study today. Okay, so let me give you a quick cartoon for the kind of calculation that we will have to do next. Yeah. Well, one way of removing it would be to it's basically subtracting that component directly from the map, yeah, so that you clean away this dipole signature. The practical way of doing that is dividing the sky into spherical harmonic components. Okay, and dipole corresponds to the L equals 2, L equals 1. 9 a.m. Okay, dipole corresponds to the L equals 1 component, and one just takes out the L equals 1 component and just doesn't make use of it. And so that's why you will see all of these CMB maps that are in L space starting at L equals 2. They start with a quadrupole because we don't think that we can actually not distinguish between an intrinsic dipole and a dipole due to our motion. Okay, in fact, that's not entirely correct. There's a way of distinguishing because there are aberration effects that would allow us to actually measure. If there was an intrinsic dipole on the surface of last scattering that's not associated with our own motion, there's a way, if you very finely measure certain aberration effects, you can actually disentangle these kind of things. There was a paper 2 weeks ago on this kind of thing. Sorry? The frame in which the CMB looks uniform, yeah, to lowest order. And, well, Okay. Okay, so let me give you a quick cartoon for the type of calculation we will have to do next. So if we consider this problem as a function of time, we will start with some initial conditions at some time ti. And as I explained last time, this is not really initial. This is just an early time during the hot phase of the Big Bang, when all modes that we care about were living on large scales outside of the Hubble radius. So at that early time, we define a primordial curvature perturbation, and it's usually done in Fourier space. So that's our initial conditions. We'll take those initial conditions to be nearly scale invariant. So that's a restriction on the power spectrum of this curvature perturbation. We will then have to evolve those initial conditions forward until a time tau star, which is the time of recombination. At that moment in time, these initial fluctuations will be related to fluctuations in the density of photons, fluctuations in the gravitational potential, fluctuations in the density of dark matter, and so on. They're all coupled to each other through the Einstein equations. And for adiabatic initial conditions, they're all related to a single initial condition, scalar mode, this zeta. This evolution we will see actually will induce some sound waves. So there's a lot of radiation pressure in the early universe. That radiation pressure leads to acoustic oscillations in this primordial plasma of photons, electrons, and dark matter. And we have to describe those standing waves. And then at the recombination, we take a snapshot of those standing waves. At some phase in the evolution, we take a snapshot, basically, but because photons decouple at that moment. Different wavelengths will have oscillated by different amounts, and so we see those different waves as different moments in their evolution. That's what we're doing here. Then we have to allow the photons to just simply free stream. So there's a period of free streaming, just geodesic motion of the photons, until they reach us at the time tau 0 today. Okay? And there's also a projection effect, because we're observing those three-dimensional Fourier modes projected onto a surface of last scattering. This decomposition into spherical harmonics will have to be taken into account here. Okay. So the first thing, what I want to do is I want to do this in reverse. The first thing I want to describe is I want to imagine, given some fluctuation spectra that we will determine in a moment at recombination, how will they propagate forward to us? This free streaming effect. So let's calculate that first. That will give us a formula for the observed delta t as a function of n fluctuations, given some not initial, but some fluctuations in the photon density at recombination. And then the next final step will have to be to relate those fluctuations to fluctuations in the initial conditions. Yeah. No. Okay, so but it's very fast. So one way of expressing it, the one I remember at least, is as a function of redshift. So recombination itself happens at a mean redshift of about 1,100. Okay, and its duration is a delta redshift of 10. Okay, so that's a measure of how fast it is, 10 over 1,000. Yeah. This finite width, yes, it leads to an extra damping of the CM fluctuations. The reason it leads to damping is because we don't know exactly at what distance the photon was coming to us. There's a spread to this, and that spread actually in Fourier space leads to damping. Okay, so yeah, that's what we have measured, this finite width of recombination in some sense. Technical term is there's a visibility function for the last scattering, which is not a delta function but has some Gaussian shape with a variance that's set by delta z of 10. Yeah.
How do we figure out which of the temperature fluctuations are both?
Well, we measure photons, so these are the temperature fluctuations in photons by definition, I think.
How are we going to talk? So the only way we're going to be able to understand how other particles affect things is by the final photon.
Yes, but there will be gravitational couplings here. This relationship between here and here will be affected by the entire matter particle content of the universe, both the standard model and beyond the standard model. And so we can look for subtle changes in the fluctuation spectra here, and then these just get evolved further. Okay, so that's what we're going to do in the second part. We're going to ask, given standard model physics and beyond the standard model physics in this period, what comes out given some initial conditions here. Okay. Okay, but first let's start here. Okay, let's start with assuming some initial some fluctuations at recombination. How do they get evolved? So we have to first study photon free streaming. And so this is a relatively straightforward exercise in GR. Okay, so the free streaming of photons is simply determined by the geodesic equation in a perturbed universe. So free streaming is determined by geodesic equation in a perturbed spacetime. Okay, so of course, famously in GR, perturbations are not gauge independent, so we have to pick a gauge in order to describe this problem. The gauge I'm going to be picking is Newtonian gauge. Okay, that gauge is defined by the following line element. So I'm going to use ds squared so previously we had this unperturbed. We had the unperturbed FRW metric like this. And so now we're going to be perturbing the G00 component and the spatial components by a metric perturbation that will play the role of a gravitational potential. And similarly here. Okay. Strictly speaking, these two metric potentials, in fact, can be different scalar functions. Okay. And in fact, in my notes, I'm treating them different so that you see how they appear differently in the equations. But in the absence of anisotropic stress, in fact, to a very good approximation, they are equal. And so for simplicity, I'm going to set these two metric perturbations to be equal. Okay, and now we just turn the crank. So you have to feed this perturbed metric into the geodesic equation. You have to also determine the perturbed form momenta of the photons. So it's a relatively tedious exercise. In fact, it takes me 2 pages, I think, in small font in the notes to do this. So I'm not going to repeat. I'm just going to tell you the final answer, which is relatively simple. But if you want to see the details, you're welcome to have a look. So what one finds at the end of the day is the following equation. So the rate of change with time of the log of the scale factor times the momentum of a photon is equal to minus the rate of change of the gravitational potential. Plus a term that turns out to be small. So I've dropped it here, but you will see it in my notes if you wish. Okay. So this is a simplified version of that final answer. But this is useful because we can now actually take this equation and integrate it along the line of sight. So we can integrate that equation from this particular point up here, from this point here, to the observer here. Just along the line of sight, we're doing this time integral. And since this is relating to total time derivatives, this will just pick up boundary terms. Yeah. So this will give us, doing the line of sight integral, will give us the log of A times momentum observed in terms of the log of A times the momentum at recombination plus the difference in the gravitational potentials at our location and at the location of the last scattering. Okay. Actually, maybe I should have explained this more. So in the absence of a gravitational potential, so in an unperturbed universe, This is 0, so this combination A times P is a constant, which is just the redshifting of the photon momentum. So P, in the absence of perturbations, will go as 1 over A. This is what this left-hand side of the equation is describing. And then this right-hand side of the equation describes an extra gravitational redshift because the photon has to climb out of a gravitational potential well and loses energy or gains energy depending on the sign of the potential. Okay? So there's just two effects here. There's a redshifting of the homogeneous that's always there. And then in addition to that, there's a spatially varying gravitational redshifting due to the presence of this gravitational potential. Okay. Okay, so far this is written in terms of the energy of the photon. We'd like to write it in terms of the temperature of the black body spectrum. But they're very simply related. So using the following proportionality, so A times P is proportional to A times T. Because we want to preserve, free streaming will preserve the black body spectrum. And it always P over T that appears in the black body distribution function. And so T has to evolve in the same way. And so we have this proportionality. And so this is the total T, so we can write this as A times T of the background, 1 plus delta T over T. And this is the combination that, of course, we're interested in. So let's solve for that. So for small delta T over T, we can expand this log. 1 plus some small quantity just becomes linear in that small quantity. Okay? So what we will find is delta T over T observed is equal to delta T over T at recombination plus the gravitational potential at recombination. And here I've dropped the gravitational potential at our location because it's unobservable. Okay? So you can always set that to 0. This is a monopole contribution in the gravitational potential. That's not observable. We can only observe the spatially varying part of the gravitational potential, which this one isn't. Okay, so I've actually chosen this to be 0. So then it will be useful to us to just rewrite this expression in terms of delta T over T observed as equals to 1/4 the fractional density contrast in photons. So this delta gamma is defined as delta rho gamma over rho gamma plus phi, both evaluated at the time of recombination. Okay. Any idea where this extra factor of 1/4 comes from when I go from temperature to density fluctuations? Exactly, because the density scales as t to the 4th. If I take differentials of this, I will pull down a 4. Okay, and inverting it gives me a factor of 1/4 here. Okay. So that tells us how to relate density fluctuations in the photon gas and the gravitational potential that's set up by all of the components at recombination to the observed temperature fluctuations today. That's a pretty useful expression to have. Okay. So sometimes this is called the intrinsic delta T temperature fluctuation. That's kind of the temperature variation that you would measure if you went there and put your thermometer at this point in last scattering. And then there's an extra shift to this because the photons travel out of gravitational potential wells and lose energy or gain energy. And so there's this gravitational redshift. And this combination is famous, so it's given a name. So this combination is also called the Sachs-Wolfe contribution. Okay. Okay, and so for the purpose of this discussion, in fact, I'm going to be assuming that this is the only contribution to the observed temperature. There's, in fact, one extra contribution that I should mention, just in case any of my cosmology friends are listening to the video. Okay. So there's an extra shift in the temperature because when the photon last scatters of an electron, so there's an electron here, the electron is typically moving with some velocity. Okay, and the photon will last scatter here. So that extra motion of the electron leads also to an additional Doppler shift of the photon in the rest frame of the observer. Okay, So you can describe the scattering in the rest frame of the electron and then transform to the rest frame of the observer, and that will give you an extra shift in the delta t. And that extra shift would be added here as a angular dependent shift that depends on the direction that you're looking at relative to the direction of the electron in the rest frame of the observer. Okay? All this I evaluated at recombination. And that contribution here is called the Doppler contribution. Sorry? How do we know VE? Through the Einstein equation. Everything will be coupled and determined in terms of the initial curvature perturbation zeta. So there will be fluid equations that couple velocity of the electrons to the dark matter density, to the photon density, to the baryon density. They all couple to each other, and they're all determined by the evolution of the initial conditions. Yeah? So these are not this is not independent from this. It's not independent from this. They're all determined by one single degree of freedom. Okay, so in principle, this is there. In practice, this turns out to be slightly smaller. And so we will get the rough shape of the CMB spectrum just by focusing on this part. Yeah? Except for points in the CMB spectrum where this goes through 0. Yeah? And when this goes through 0, then the 0 points are filled out by this Doppler shift, because it turns out this Doppler contribution is actually shifted by pi over 2. And so wherever this goes to 0, this has a maximum contribution. But as you can look at my notes to see these contributions split up, and you will see that this dominates for most of and the basic shape of the spectrum you get by just looking at this part. So that's what we're going to be doing. We're going to ignore this extra contribution. Okay. Okay, so this was a useful formula, but not quite yet what we eventually want, because what this is telling us, it's telling us the contribution in one given direction in the sky. Okay, and what we really care about is correlations. So what we'd like to know is if we look at two separate directions in the sky, so n hat and n hat prime, how are these things correlated as a function of the angle theta between the two lines of sight? Okay, and so that's quantified by the power spectrum, so CMB power spectrum. So in particular, we'd like to calculate the two-point function of delta t in the direction n, delta t in the direction n hat prime. This is often expressed in a harmonic decomposition. So we can write this as 2l plus 1 over 4 pi cl, and then a Legendre polynomial of order L of the cosine of the angle between these two lines of sight, summed over all of the harmonic moments from L equals 2 to infinity. Okay. So this is a Legendre polynomial. And these coefficients CL here are the angular power spectrum. Okay, so the collection of all of these harmonic coefficients, CL, contain all of the information about the two-point correlation function of this real space map, delta t of n. That is because I've only started the sum from L equals 2. Exactly. So that's, in fact, the most efficient way of subtracting the dipole is by restricting the sum. Yeah. Okay, so a rather longish exercise now is to substitute this expression that we had for one of the line of sights twice for each of these contributions and do some algebra. And I've done the algebra for you in my lecture notes. Okay. So substituting this Sachs-Wolfe contribution gives the following result. So CL, so let me write it out and then explain it. There's a convention factor that's a 4 pi up front, 2L plus 1 squared. Of course, I could have chosen slightly different conventions here, and this would have just been absorbed into a redefinition of this power spectrum, but my definition has this extra 2L plus 1 factored out, and so that will just crop up again in various places. So then this is written as an integral over all Fourier momenta, JL squared KR star T squared of K and the power spectrum of the initial conditions. Okay? This is not completely trivial to do. This takes about 2 pages to derive from going from here to here. I wrote it in 1 page because I was slightly lazy and I skipped a few steps. If you want to write all the steps, then maybe it's 2 pages to get to this. But the structure of the formula is rather simple, so I want to focus on what this equation here is telling us rather than the algebra of getting there. Okay? So you notice, first of all, it's an integral over the initial conditions, when written in Fourier space. So here the initial conditions appeared. There's a function of k that determines how a given Fourier mode in the initial conditions evolves towards the surface of last scattering. So that function here describes the evolution. And since it's linear evolution, this function is simply the ratio of 1/4 delta gamma of k at tau star plus phi of k at tau star divided by zeta of k. Okay? And because the evolution is isotropic, in fact, although the initial conditions are directionally depend on the vector k, and the final variables are also directionally dependent, the ratio of the two, which determines how the initial conditions evolve towards these final fluctuations, that's independent of momentum direction, and so that's why this function here is only a function of the absolute value of this k mode k, momentum mode k. Okay? And in fact, it will occupy us for the rest of this lecture a little bit to how to determine this function t of k. And then this final function here is a spherical Bessel function, which describes the projection onto the sphere. Okay. In fact, let me give you a little bit of intuition for the appearance of this spherical Bessel function. So going back to this picture here, imagine I had a single Fourier mode in the initial conditions, so a single Fourier mode in the fluctuations at recombination. Okay, and that Fourier mode here is aligned vertically, and I've shown like wave fronts, maxima basically of the single Fourier mode. But this single wave is now evaluated at different points on the surface of last scattering. So in particular, whenever a maximum of the wave crosses last scattering, that's where we would see a hotspot. And in between, there will be minima, so there will be cold spots in between. Okay, so you see that even for a single three-dimensional Fourier mode, you get variation as a function of angle. Okay, with a characteristic scale that depends on the size of the wavelength of this Fourier mode. So there's a variation with angle here. Okay, and this Bessel function is what's formally doing that projection from k space to angular variation, so L space and harmonic space. Okay. Now, in fact, if you take out Mathematica and you were to plot, and I should explain the argument of this Bessel function. So you notice this r star that appears in the argument of the Bessel function. That's simply the distance from us to the surface of last scattering. here. Okay. So that projection effect does depend on how far away. Of course, you can actually try and redrawing this sphere with a bigger radius, and you will see the projection changing in a certain way. Okay. Okay, but now if you take out mathematics and you were to plot the square of the spherical Bessel function as a function of its argument kr star, it looks something like this. So it has a prominent peak when the value of kr star matches the order of the Bessel function L, and then it has higher order rapid oscillations afterwards. Okay. And so what we have to do, in fact, is we have to take the initial conditions evolved through this transfer function and then integrate it against this Bessel function. But that integration will act like a delta function if we just focus on this prominent peak here. So Bessel acts like delta. Okay. So if we make this very crude approximation of the Bessel function acting like a delta function, we can in fact write the angular power spectrum in the following simple form. It's simply this transfer function squared when evaluated at a k value that's approximately equal to L over R star. Okay. So the reason the initial conditions don't appear here anymore because I've assumed perfect scale invariance, so they're actually independent of momenta. They will just set the overall scale of this power spectrum. And so the only momentum-dependent function that's left in the integral is this evolution that depends on momentum, so this transfer function. And then the delta function means that I should be evaluating that transfer function at a specific value of k that corresponds to the harmonic mode that I'm interested in when rescaled with the distance to the last scattering surface. Okay? Okay. But this is kind of nice because it's telling us that the observed CMB spectrum that we all know and love, this kind of famous shape for CL, is really just a reflection of this momentum-dependent evolution when taking into account this projection onto this guy. Okay? So by understanding this function t of k, we will understand everything. Okay? So that's the last thing we want to do today. Any questions about this? So I hope this is not too fast. This can easily take 5 lectures. Sorry? I've assumed that this is a scale invariant function, so it doesn't depend on momentum. And so then this is just a number, which is 10 to the minus 10. So that 10 to the minus 10 will just pull out, and I've not written it there. I should have maybe. Okay? So this is just a proportionality that I'm writing over there.
So it's kind of a postmodern way of looking at things. The old days people would say, oh my God, it's a scale invariant. You're saying it is what?
No, I could keep it. So if you keep it, nothing much changes. I just have to put the p zeta here, evaluate at k. And in practice, of course, people are very interested in small, so this will lead to a slight tilt of this spectrum here, and we have measured a slight tilt. In fact, it's very exciting and so on. So I don't want to belittle kind of this extra factor here. But just at the moment, we're just interested in understanding the rough shape. Why does it have these type of oscillations and so on? And what happens to these oscillations when I change the physics of the evolution equations? Okay? And for that purpose, this extra contribution here is less interesting because it's so nearly flat. Any other questions? Okay. So we have almost understood everything except for this function t of k, which I've defined but not really derived for you yet. And so the last thing we want to do is deriving that function. So in principle, this is a relatively complex problem. So what we want to study is sound waves in the primordial plasma that are being, evolved under the influence of gravity. And so a cartoon that's kind of nice to summarize the nature of the problem is the following. So we will have to evolve the metric g mu nu in response to all of the matter components in the universe. And so what are the matter components? So we have photons, we have electrons, we have protons, we have dark matter, we have a cosmological constant, but at early times that's irrelevant. We have neutrinos, and maybe we have something extra that we don't know yet. Okay, all of those things interact via the Einstein equations with the metric. But at different times in the history of the universe, some components are more important for this back reaction on the metric than others. Okay, so for example, at early times, photons and neutrinos, which we combine into all of the radiation, is dominant gravitational effect on the metric. At later times, dark matter will take over and become the dominant gravitational source. Okay, and maybe at early times there's some small contribution from some extra species X. Then some of these components here are directly coupled. So photons and electrons are strongly coupled by the electromagnetic force, and electrons and protons are also strongly coupled to each other. Okay, and that's why this system here of electrons and protons, which we call baryons, and photons, is often, for most of the history of the evolution, is treated as one single fluid of photons and baryons. Okay, it's called the photon-baryon fluid. So what we'd like to understand is how does the fluctuations in the photon-baryon fluid evolve under the influence of gravity, where gravity is set up by in dark matter and photons. Okay. Yes. Well. I think for the modes that we care about, it doesn't matter. That most of the evolution actually happened afterwards, and so they were frozen before. And so the frozen evolution is, of course, very easy to describe. We just translate the initial condition to some later time when it enters the horizon. And this type of evolution will then play an important role once sub-horizon evolution leads to these oscillations. Okay. So the way I want to simplify the problem, just so that we can do it on the board in real time, is I want to focus on short modes. So this will get things slightly wrong, on the larger scales, but will start to become a better and better approximation as I'm starting to sample higher and higher peaks in the spectrum. So we'll get all of the features here, pretty good, yeah? But it won't get this plateau region exactly right. For that, I would have to look at slightly more involved equations. So what's true for short modes is that most of the evolution takes place when the universe was radiation dominated. So it takes place in the radiation era. So there's an important fact that short wavelength fluctuations enter the horizon earlier, okay? And so therefore they spend more time inside of the horizon during the radiation dominated era. The universe becomes matter dominated just shortly before recombination. It's actually a pretty small effect. So it becomes matter dominated as a redshift of about 3,400, while recombination is at a redshift of 1,100. So that's a relatively short period of matter domination, and we're going to be ignoring that short period of matter. Going to basically be pretending that the universe is radiation dominated until recombination. Okay? But that will still give us the basic features, right? And in fact, the shorter the wavelength of the initial conditions is, the better that approximation will become. So what's nice about making this approximation, there will then be a single master equation that describes everything. And so that master equation is an evolution equation for the density contrast of photons, which takes the following simple form. Okay, what this CS here is called the sound speed, and it takes an approximate value of 1/3. It's basically determined by the equation of state of the radiation pressure, okay, which is 1/3. Okay, so this is kind of neat. This is a harmonic oscillator equation that describes how the density of photons evolves as a function of time in the response to the gravitational force. So there's a gravitational sourcing on the right-hand side. there's a pressure support. Sorry, this should be a Laplacian. So the density variations lead to pressure, and so there's a pressure support that tries to resist the collapse of these density fluctuations. So in the absence of this, density fluctuations would just collapse and clump, okay, like they do in the late universe for dark matter. But now here there's a pressure support due to the pressure set up by the photon gas. And so as we're trying to compress the gas, it will respond by going outwards, and so it will lead to oscillations. And that's the famous equation that describes these oscillations. This equation? Actually, no. It's more closely related to kind of the conservation equation of T mu nu. So if you take the combination of photons and have to include the baryons also, although this approximation actually is not so important, then this conservation for the photon gas, this conservation equation leads to this. Okay, there will be an extra Einstein equation that determines how phi evolves in response to everything else. Yeah. So the 0,0 component leads to some kind of Poisson equation for the gravitational potential that we also have. Yeah. Oh, we'll get to this. Yes. Yeah. So this equation, yeah, good point. This misses still two important effects that I'm going to come back to. Okay, and one important effect is dissipation. Yeah. So we have kind of pretended here that photons and baryons are a perfect fluid. And that's on long wavelengths, sufficiently long wavelengths larger than the mean free path of the photons. That's a good approximation, but of course we should be correcting these equations. And we can do that order by order in some ratio of wavelength to the mean free path. And that will lead to, in fact, effective viscosity terms in these equations. Yeah, this will come up. Okay. Okay, so let's try to solve this equation. So it turns out I can write down a solution directly for the combination of photon fluctuations and gravitational potentials that I care about. And basically because, if you look at this equation and you substitute 1/3 for the sound speed, then you notice that if I move this to the left-hand side, okay, it's precisely this combination that appears underneath the Laplacian. Okay? And then it turns out that on small scales, the time variation of this gravitational potential is a subdominant effect. So I can even incorporate this gravitational potential inside of the time derivative. And then I just get a free harmonic oscillator equation for this combination. And I'm just going to write down the solutions of the free harmonic oscillator. Okay, as simple as that. Okay? And of course, the solutions are cosine and sine. So we've got two solutions, but as different solutions for the different k modes in principle. So there's an amplitude of a cosine CS k times tau plus an amplitude for the sine CS k times tau. Okay, and we're doing this in Fourier space. So in principle, we are allowing for different amplitudes for each of the different Fourier modes. Okay, and then this cosine and the sine describes how each of these different Fourier modes is evolved forward in time. All right. But let's also remember that we're focusing on the case of adiabatic initial conditions. So it turns out one property of adiabatic initial conditions is that they lead to analyticity at early times, or in the limit of k going to 0. And this sign contribution is not analytic in the limit k going to 0. So adiabatic initial conditions, in fact, don't allow this sign. So for adiabatic, and since most inflationary models, in fact, predict adiabatic initial conditions, they also predict that we should be seeing a pure cosine here rather than a mixture of cosine and sine. Okay? And in fact, when we look at the sky, we do see a predominantly cosine contribution, or there's no evidence for any admixture of a sine here. And so that's taking us strong evidence for this adiabaticity in the initial conditions. If I go to the superhorizon limit and in fact do the matching exactly, I can also determine how this amplitude here is fixed by the initial amplitude of curvature perturbations. And it's just a factor of 3 that relates them. So this is 3 times zeta of k of cosine CSK of tau. Okay? So now if I want to relate this to this function t that I've defined here, I simply have to take that solution and evaluate at the moment of recombination at tau star. Okay? So this means that this transfer function t of k is taking this solution, evaluating it at tau star, and dividing it by zeta of k, which was the initial conditions. So that will give me 3 times the cosine of s star times k, where s star is defined as cs times tau star, and it's sometimes called the sound horizon. This is a specific transverse length scale that's defined at the surface of last scattering in terms of my cosmological parameters. They will determine the sound speed, which in this approximation here was in fact just a constant, and they will determine in fact at what moment in time recombination occurred. And so that's a specific scale that we can look for in the sky, okay, because it appears here in this transfer function. Okay? But now we're done, okay? Because this was the missing piece that allows us to relate the CMB spectrum. So this will tell us that CL is 36 pi over 2L plus 1 squared cosine squared of S star times L over R star. Okay? So the main oscillating features that you're seeing in the CMB spectrum is simply this cosine here that comes from the evolution of a Fourier mode in the primordial plasma. Okay. All right. One thing you can read off from the solution is that it will have peaks, at the peaks of this cosine here. So there will be peaks at multiples of L star equals pi R star over S star. And both R star and S star depend on cosmological parameters. So by measuring the locations of the peaks on the sky, we will indirectly constrain the cosmological parameters that go into these functions. So for example, the effective distance to last scattering depends on the total matter density in the universe. This horizon size here depends on a combination of things, okay, that we could track down later. Okay. The other thing that's important is that these peaks have been measured very accurately. Yeah. So these peaks are measured to an accuracy of 0.05%. Okay. So you would not like to introduce new physics in the early universe that completely changes this peak-like structure, because it's one of the best measured things that we have in cosmology. Okay. This kind of accuracy is unheard of in cosmological measurements, and so whatever changes we make to the early universe physics that changes the CMB spectrum, it better keep intact the locations of these peaks. Okay. And so that will be a constraint later.
That's why we can't fiddle with dark matter.
Well, you can fiddle with dark matter, but you have to simultaneously rescale something else. So you can fiddle with dark matter if you're also changing the Hubble constant, for example. And so it's a highly constrained, but then changing the Hubble constant will screw up something else. So you're really in a straitjacket where we know things about the late time matter density, and we know things from supernova about the expansion of the universe. And so it's highly constrained. And that's why we have so good constraints on the combination of many parameters. But yeah, it's degenerate. There are certain degeneracies. So in fact, the famous degeneracy called that geometric degeneracy. If I change omega matter, So it turns out this peak location for a flat universe is a function of omega matter times little h cubed, where little h is the dimensionless Hubble constant. So this particular combination appears, and you can see analytically why. So if I change omega matter, but I'm simultaneously rescaling the Hubble constant by precisely this power, then I keep things exactly the same. Yeah. And so that's a. This one? This L here, you mean? Well, except that, of course, both of these parameters depend on choices for my background cosmological parameters. So there's. No, because this, for example, R star, yeah, is a function of the matter density, is a function of the Hubble constant, and other things. Maybe the curvature, if you're allowing curvature. And so I should allow these as free parameters that I'm also fitting. So typically, this curve here is fitted by 6 parameters. Okay, there are 2 parameters in initial conditions, which is the amplitude and the scalar tilt. Okay, and then there are 4 parameters that describe the composition and geometry of the universe, and that's typically chosen to be the dark energy density, the dark matter density, say the Hubble constant, and then some strange parameter that describes stars. Okay, which is called optical depth. Which describes a slight rescattering of the photons as they travel through the universe, which we haven't included here. Okay, so those are the 4 parameters that you have to include. But that's it. So you have 6 parameters, and you're fitting a couple of thousand multiple moments, and including the testing for non-isotropic, and their magnetic counterparts. So actually, there's 10 to the 6 data points in some sense that you're fitting with 6 parameters. Yeah. This one? Yeah. Yeah, that's true. So of course, we should then still remember that this is we have made a couple of brutal idealizations here. And so in fact, in the next 15 minutes, I'm going to mention how this has to be improved. To change this will change the transfer function slightly. And those changes to the transfer function will give you sensitivity to additional parameters. So yeah, I totally see that you don't expect to fit 6 parameters with this, or extract 6 parameters with this simple function. But there are more features. For example, what I haven't included is actually the weight of the baryons in this photon baryon fluid. That weight leads to a slight shift of the equilibrium of these oscillations. And so that actually leads to odd and even peaks in the CMB spectrum to have slightly different amplitudes. And that allows us to measure actually how many baryons there were in the early universe. Then, as I'm going to mention in a moment, we haven't included viscosity. That viscosity also depends on these cosmological parameters in different ways here. So it's true, yeah, of course, this is not how data analysis is done. Okay, this is just to try and understand the basic features. Yeah. This one, yeah. Yeah, this is not great for that region because we have assumed that there's no matter-dominated period and so on. So we can do, but you can do better analytically with a little bit more work. It might take us 2 lectures if we wanted to do this more properly. Okay. No, this peak here happens at an L of 100, roughly, and then we're measuring peaks up to 4,000. So I've accurately described, roughly speaking, say from L of 300 to 4,000. I've done a pretty good job in approximating things, and I have done a worse job for the first 100, 200 multiple moments. Okay, but that's also where the shape of the spectrum is kind of boring. This flat part of the spectrum is just the initial conditions. So actually, you can easily show that this transfer function T of k just approaches a constant if the mode has never entered the horizon. This is what these modes here are doing. These modes here were always outside of the horizon. They didn't evolve. This transfer function is boring as hell because there's no evolution for all of the k modes. So it's just a remapping of the initial conditions. So it's not that we can't understand what's happening here. In fact, it's easier to understand what's happening here than what's happening here. Okay, and we could patch the two together analytically if we wanted. Yeah. I don't think so, because if you had pure isocurvature, you wouldn't get any oscillations. Yeah. And so therefore, you get actually a lot of constraining power on isocurvature from the oscillations, because they shouldn't be there if it was pure isocurvature. So I think it's mostly the short scale modes that constrain isocurvature. Any other questions?
So this one going down or like half smaller amplitude with L is just the 1 over L squared in front?
No. No, actually, sorry. When we're plotting this, we actually have to put we usually plot L times L plus 1 times CL. So we plot, roughly speaking, L squared times CL, which will actually put the 1 over 2L plus 1 squared to the other side. So if there was no oscillations, if there was no cosine, we would expect the CMB spectrum in this way of writing it to be exactly flat and just be a remapping of the flat initial conditions. So this, yeah, I've taken care of that by putting it to the other side. Okay, what I'm going to mention next. Okay, so as I already alluded to, so our solution still misses two important effects. So the first omission was that we've pretended that the universe was always a perfect fluid of photons and baryons, and that's not the case on the shortest scales, distances shorter than the mean free path of the photons. So we have ignored so-called diffusion damping. So as a cartoon, if you imagine gas of electrons with a specific separation between them, and photons that are scattering off these electrons, these photons have a mean free path lambda c, which scales as 1 over the number density of electrons times the Thomson cross-section for the scattering times the scale factor. The scale factor only appears because I'm describing things in co-moving coordinates, and so to go from physical mean free path to co-moving mean free path, that picks up an extra scale factor. Number density of electrons appears because, of course, the higher the density of electrons, the shorter the mean free path. So that has the right scaling here. And the higher the scattering cross-section, also the shorter the mean free path. So that describes the scaling of this mean free path. So we would expect this treatment that we have done so far to work reasonably well at wavelengths that are larger than this scale here. But to fail completely, not completely, but have to be modified at wavelengths that are smaller than this mean free path. And intuitively, what will happen on those very short scales is that on those short scales, the photons can random walk in between the scattering events, okay? And they can random walk from hot regions into cold regions and redistribute the energy density of the photons. And so that will erase some of the fluctuations, okay? Just because of a random walking of photons in the gas that's set up by electrons and protons. So we can estimate the length scale associated with that diffusion. So that diffusion length, lambda d, is proportional to the mean free path times the square root of n, where n describes the number of steps that the photon is taking in the random walk. And the number of steps it takes is proportional to the time that it has to execute that diffusion, divided by the mean free path. That tells you the number of steps that the photon is taking, times the mean free path. And so that gives us a square root of the time times the mean free path. Okay? So this diffusion length is given by the geometric mean of the horizon scale at a certain time times the mean free path. Yeah? And so if you incorporate this effect via some viscosity in this equation of motion and then solve that equation of motion, what you get as a change to the transfer function is the following. So this transfer function t of k on large scales will be the same as before, and large now measured relative to this diffusion length, it will still be a cosine. But then on smaller scales, then this mean-free path, it gets exponentially shut down. So there's an exponential envelope to the solution, which is e to the k squared over kd squared, where kd is just the momentum scale associated with that diffusion length. Okay? So there's you expect an exponential drop in the spectrum for wavelengths that are smaller than this diffusion length, and that's what this exponential envelope here is describing. Okay? And it's this exponential cutoff that explains why the CMB spectrum drops off after a certain value of L. Okay? And in fact, by measuring, but that diffusion scale here depends on parameters, and in fact, it depends sensitively on the number of free streaming relativistic degrees of freedom, like neutrinos in the early universe. So by measuring when this kind of drop in power occurs, we actually gain some information about extra light species. Okay? So that's why it's important to incorporate this in our thinking, because it's going to be one of the main physical effects that make us sensitive to new types of physics that are light and weakly coupled. All right. Sorry? Tau is conformal time. Okay. So what is this? This is the number of steps that the photon is taking while random walking through this gas of electrons. Okay. And so it of course takes a step. It scatters on average at every mean-free path, and in a time tau, it will execute n times lambda c as a distance. Okay, so I'll have to sketch the rest because I only have 5 minutes left. So let me not write everything that I've prepared to write, but let me just give you the gist of the story. So the second effect that we're missing is that there's a subtle phase shift in the solution. So I've told you, I've erased the equation now, but I told you earlier that we were moving the gravitational potential to the left-hand side to transform this forced oscillator equation into a free oscillator equation for the combination that appears in the Sachs-Wolfe contribution. But what I had to do in order to do this is I had to assume that time derivatives of the gravitational potential are small. And it actually turns out if I couple the gravitational potential to neutrinos and maybe an extra species X, the condition is I couple it to anything that has an intrinsic speed of propagation, so c of x, say, that's larger than the speed of sound of photon fluctuations. So as soon as this condition here is satisfied, it creates a phase shift in the solution. Okay, so the solution, or the transfer function t of k will go to cosine of cs star of k plus a momentum independent shift phi star. Okay, and the size of this momentum independent shift depends on the energy density of extra species that are coupled to the gravitational potential via the Einstein equations. Okay. Okay. So it breaks my heart to cut this down like this. I wrote an entire paper about this last year. I'm very proud of it. You should read it. But this is as much as I have time to say about it. Okay. I write it out in my lecture notes, so you can actually see the derivation if you want to. Okay. There's even complex analysis in there, so it's nice. But okay, no time. All right. But the upshot of all of this, and this is the last thing I want to say, is that by measuring the amount of damping and the shift in the phases of the oscillations, we probe extra light species. Okay. And in fact, so future CMB experiments so there's an entire program called CMB stage 4. At the moment, we're entering CMB stage 3.5 or something like this. Okay, so the next 5 years or so, people are building, telescopes with more and more detectors. So basically, what the plan is just brute forcing your way to higher sensitivity. So there's actually a Moore. If you look at my notes, there's a nice plot that I like, which is some kind of Moore's law for the sensitivity of CMB experiments as a function of time. So if you just ask no improvement of detector technology, just adding more detectors onto a telescope. So going from 10 to the 2 detectors to 10 to the 3 detectors to 10 to the 4 detectors, 10 to the 5 detectors. I think this is 10 to the 5. Okay, if we can package 10 to the 5 detectors with the same technology that we have today onto a telescope, it will reach an order of magnitude higher sensitivity to these type of effects, and so will give us constraints on delta and effective at about the level that's interesting for this type of decoupling at very early times. Okay. So what this means, okay, is that either we have to see something. If these particles exist and have ever come into thermal equilibrium, we will have to see them. Okay. And even if not, if we don't see them, it will put very strong constraints on the couplings to the standard model. Okay. And so if I had more time, I would go through this. But what you can do is you can write down an effective field theory of light particles coupled to the standard model. So you can write down an effective Lagrangian of all operators made out of some new light degrees of freedom x, coupled to the degrees of freedom of the standard model with some coupling strength lambda and some scaling dimension delta that depends on the scaling dimensions of these operators. In order to make these particles here naturally light, we can impose additional symmetries, or we should impose additional symmetries on these particles. And we can then classify all of these interactions according to spin. So for spin equals 0, we're going to consider Goldstone bosons, or axions. Spin 1/2, it's easy to have naturally light fields because of axial and chiral symmetries. Spin 1, it's easy to have light fields because of gauge symmetry. Spin 2 is also easy, but these particles, if it's the graviton that's the unique spin 2 particle that's light, then it's very hard to couple it so strongly that it's ever in thermal equilibrium. So that's usually where we stop. But that's why I was showing you, spin, actually there's spin 3/2 for the gravitino. It's also interesting, because the gravitino often couples not with gravitational strength, but with the strength of the SUSY breaking scale, because there's an equivalence theorem that relates the gravitino couplings to the Goldstino couplings. All those kind of things we could discuss if I had more time. Okay. But what it means is not seeing something means you put some strong constraint on this scale lambda. So for example, just to make this concrete, if I take an axion and I couple it to photons, so axion coupled to the field strength of the photon and its dual, that's a shift symmetric dimension 5 operator. It's shift symmetric despite appearance, because when I choose this to be a constant, this combination here is a total derivative. Okay, so it satisfies the shift symmetry for the axion. That's why the axion is naturally light. So then I can convert this lambda coupling to photons into a decoupling temperature. And I can ask that this decoupling temperature is larger than the reheating temperature of the universe. If that's the case, it effectively means that this particle has never been in thermal equilibrium. At the time when the hot Big Bang was created, the interaction strength with the standard model was already weak enough for expansion to dominate. Okay, so this would not get this type of coupling for large enough lambdas will not allow for thermal abundances. And so you can ask a constraint at this order of magnitude. What does it translate to into a constraint on this coupling? And so what you find is that this lambda has to be bigger than 10 to the 13 GeV. And then there's a dependence on this reheating temperature. So for a reading temperature of 10 to the 10 GeV, that's the order of magnitude that you get. Okay. And let's compare this to what I told you, how well this coupling is constrained at the moment from stars. So compared this constraint that we had at the beginning last time, which was 10 to the 10 GeV. So there's an opportunity of getting orders of magnitude improved constraints on these axion couplings from the CMB itself. Okay, and in fact, this axion photon couplings is actually one of the best constrained couplings. So for other couplings, we will get even much better improvements on constraints. Okay, but so you can look this up in the notes, but I should better stop here. Yeah.
So in your claim, it's easier with nitrate overlation for higher harmonics. But
yes. Yeah, good. Yes. Actually, I should clarify your statement. Okay. So it's easier on the board, with a few twiddles and a few lines of algebra to do analytically the short scales. Yeah. With computer codes, it's no problem whatsoever to predict analytically all scales. So you just have to solve coupled Boltzmann equations and fluid equations and so on, and the Einstein equations. And that's there's no theoretical uncertainty. I don't want to give that misimpression. Okay, it's just for simplicity's sake we were focusing on those scales. Okay. Then coming to the second part of your question. So the reason, it's true that if you look at the error bars on this curve, they start to shrink. They scale inversely with the harmonic moment L. And they get smaller and smaller on short scales. And that's basically because there's an intrinsic error associated with each of these points, coming from the fact that we only have a finite number of samples to look for. For L equals 2, for example, you have 2L plus 1 magnetic moments that you will be sampling. And so as you go to higher and higher L's, you have more and more samples of that harmonic mode. And there's an intrinsic so-called cosmic variance that we're coming from the fact that we only have one sky to look at. And we can't, for small scales, we can overcome the fact that we have one sky by dividing the sky into smaller patches and measure the spectrum of each of these patches. For the smallest L's, that's not the case. So for L equals 2, the sky is just divided into 4 patches. And so we don't have that many copies of the single sky to observe. Okay? So that effect is called cosmic variance, and it's added to these error bars. So this also means that no matter these at the moment, these measurements here are cosmic variance limited. So the error bar that you're seeing here is mostly just coming from this effect, up to an L of, I think, 2000. Okay? So up to L of 2000, no matter how good of an experiment we build, we will not do better in measuring these temperature fluctuations because they're limited already by the fact that we only have one universe to observe. Yeah? Yeah. Sorry, say again. Yeah. Yes. Exactly. Yeah, exactly. So, okay, thanks for the question. Okay. Yeah. Yeah. Good. So there's a second one I could have written, which is the couplings to gluons, which is interesting precisely for the QCD axion because it's precisely the one that has to be there in order to solve the strong CP problem. So we could, so there's a similar coupling to this, just tracing over the gluon field strengths. Okay, and that coupling is actually much weaker constrained by dipole measurements. So electric dipole measurements actually constrain that coupling. And it's relatively weakly constrained. And so what we found there is that the CMB would give us constraints that are 9 orders of magnitude stronger than current constraints coming from dipole measurements. Okay, and that coupling is very interesting, of course, for the QCD axion because we know it has to be there. This coupling here for the QCD axion is model dependent, and it depends on what flavor of the day of the QCD axion you prefer. But it definitely has to be the coupling to gluons, and so it would be interesting to get better constraints. And I think there are 9 orders of magnitude hidden in CMB measurements.
Can I for a coffee break.
Yeah. Right.
Really, great blackboard.